Alrighty. Happy Pie Day. No, I didn't bring you pie. But I did, or Mr. Roth put a nice joke for you on there. Why should you not let advanced math intimidate you, Brooke? It's really as easy as pie. Okay? You told him, Paul?
Yeah.
Good job.
He's making that up.
I know he is, but we can still make him feel good about himself. Okay? So, what do you guys think about that graph? That's an actual thing. That's an actual graph.
You didn't just doodle that?
I did not just doodle that. That is an actual graph.
Oh, God. I don't like it. It's not a function.
It is not a function. Why is it not a function?
I mean, it doesn't pass the vertical line.
Doesn't pass the vertical line test. What about its inverse? Is its inverse a function?
No.
No. Doesn't pass the horizontal line test. Okay? So it's really not a function. We call it, though, a parametric equation. And we're going to start a section today about parametric equations. Okay? Now, you're used to Cartesian equations. An equation for a line, y equals mx plus b. An equation for a parabola, y equals ax squared plus bx plus c. Okay? A cubic, so on and so forth. It would have a cubic term in it. All that stuff. You've seen those all. Okay? We've also seen conic sections. Okay? Parabolas, circles, ellipses, and hyperbolas. Okay? So we've seen a lot of different equations. A new type of equation that we're going to see today is something called a parametric equation. And that right here, this is the equation for that graph that I just showed you. Upon just glancing inspection, what can you tell me looks different about a parametric equation as opposed to just a regular old equation? Anything that looks different? Shout it out when you think you got one, or when you see something that looks different. From something, for instance, like if I had a line, I'm talking the difference between that and like y equals negative 2x plus 1, or y equals negative 1/4 x squared plus x minus 3. Between a line and a parabola and this parametric. What looks different? What do you got? Okay, but we've graphed sines and cosines before, right? Right? Okay. So that's not necessarily different because I could have done over here, I could have done y equals cosine of x. Right? And we've graphed those before. So that's not new. Lots of people have said that's been different. It's got sine and cosine in it. We've done those before. What else looks different?
X is like on the left side of the, I'm going to say like X and Y. Like the function of something else.
So x is defined as a function, and y is defined as a function. Okay, like that. That's definitely different, where each variable is defined as a different function. Okay, anything else? What else you got?
What is part is like a restriction of points.
There's a restriction. Okay, so we like limit where the function goes. Okay, but yeah, so instead of taking a whole graph, we're just going to take a sliver of it now. Yep, okay. One other thing that's probably so It's out there and it's hitting you in the nose and you probably don't even feel it. Because you're trying to look at something even deeper. Well, yeah, 'cause that goes back to what Rachel was saying, was that x is defined as a function, y is defined as a function. Eh? How many variables are there now? How many variables? 3. Okay. All of a sudden now there's 3 variables. Okay. So let's talk about the difference between all of these. So let's go old school first. Okay. An old school function, y equals f of x, has where we take the x, and that is our independent variable. Because what we do is, if we don't know what the graph looks like, we pick different x's, then we plug those into our function, and we get out y values. So that makes x be our independent variable, and that makes y be our dependent variable. Okay? And then we plot all of the x comma y points, or we really plot x comma the value of our function at x. So we plot x comma f of x. Okay? And you've been doing that for years. Okay? You probably started that before you even got to Wausau West. Okay? You've been doing that for years. Graphing lines, plotting points, etc. Okay? Today, it all changes. Because now we've got 3 variables in there. First off, the new variable t we call the parameter. Okay? We call t the parameter. It is now our independent variable. Which then makes, because t is what I'm going to put into my function for x and get out my x value, t is what I'm going to put into my function for y and get out a y value, and so that makes x and y both be dependent. I'm still going to plot points because I still want to get those graphs. So I'm still going to plot my points x comma y. But now, really, I'm plotting f of t comma g of t. You probably don't realize it, But you've been working with a parametric equation for the better part of 3 months. What have we been working with for the last, 3 months? Unit circle. The unit circle is a parametric example. Our parameter on the unit circle, t, is theta, our angle. Which makes my function for x be the cosine of t. Which makes my function for y be the sine of t. If I pick an angle somewhere between 0 and 2 pi, let's say I pick 7 pi over 6. Okay? So t is equal to 7 pi over 6. My x value would be the cosine of t, which would be negative square root 3 over 2. My y value would be the sine of t, or the sine of 7 pi over 6, which would be negative 1/2. So I would plot the point negative square root 3 over 2, comma negative 1/2, and I would be right there on the unit circle where this dot is. Okay? And if I continued that, I would get all of my points around the unit circle. Okay? So we've been working with a parametric function or parametric equation for a while. Okay? So, in order to graph a parametric equation, I have to give you, or we have to give you, 3 things. Wait, how did it clear up? The fog is burned off. In the last class, you couldn't see the climbing wall. Yeah, that's how thick the fog was. Okay? All right. So the 3 things that I have to give you are, that's my up moment. Squirrel. First thing I have to give you is I have to define what x is. So in this case, I've defined x as t squared minus 9. Okay? I have to give you a function that defines x in terms of t. Second thing I have to give you is I have to give you a function that defines y in terms of t, which I did as y equals 2t plus 1. And then the third thing that I have to do is I have to give you an interval, and this is very important. I have to give you an interval of t values. Okay? So these are going to be the restrictions on t, or the t values that I want graphed. Okay? So we're only going to put values of t in between -3 and +2. We're not going to go any further on either side. So what that means is I am going to start by plugging in -3 for t. I'm going to stop by plugging in 2 for t. Now, I like to make it easy on myself. Okay? I'm a path of least resistance type of person unless I have to go off the beaten path. Okay? So I would pick points in between there, like -2, -1, 0, and 1. If you wanted to be one of those people that put in -1.5, hey, more power to you. Okay? Probably not going to come out nice and pretty. Have a sharp pencil. Okay? If you wanted to be one of those people that put in 1.8765309, again, that's all on you, not on me. Okay? So, now, I'm going to start by putting in -3 in my x function. -3 squared is 9, minus 9 is 0. -2 squared is 4, minus 9 is -5. -1 squared is 1, minus 9 is -8. 0 squared is 0, minus 9 is -9. 1 squared is 1, minus 9 is -8. 2 squared is 4, minus 9 is -5. So I found all my x values. Now I'm going to go back and I'm going to put in those same t values in my y function. -3 times 2 is -6, plus 1 is -5. -2 times 2 is -4, plus 1 is -3. -1 times 2 is -2, plus 1 is -1. 2 times 0 is 0, plus 1 is 1. 2 times 1 is 2, plus 1 is 3. 2 times 2 is 4, plus 1 is 5. So I've got all those values. Now, those correspond to points that I can graph. So this first one, I'm going to graph the point 0, comma, -5. 4 and 5. This one corresponds to -5, comma, -3. 2, 4, 5, 1, 2, and 3. This one, -8, -1, 6, 7, 8, -1. Here, -9, comma, +1. Here, -8, +3, and 3. And lastly, -5, comma, +5. Now I can connect those dots with a nice smooth curve. But notice, even as much as my pencil or my pen, or in this case my marker, wants to go past those points, I don't. My graph will stop on both ends. It's only going to be a portion of my function. Don't put arrowheads on the end. Don't go past your endpoints. Okay? Your graph will stop. Okay? And I want it to stop. Okay? Now, mathematically, I can take my parametric function and I can do something called eliminate the parameter with it. When I say eliminate the parameter, I want to get rid of t. So my original function again was x equals t squared minus 9 and y equals 2t plus 1. If I am going to eliminate the parameter, I need to solve one of those two equations for one of those three variables. And then I'm going to take that and put it into the other one. Unfortunately, I can't solve for x or y, because in the opposite equation, or in the other equation, there is no x or y to substitute into. So that leaves me with one real choice, and that choice is I need to, oops, Tapeth breaks. I need to solve one of the equations for t. So my choice is in the x equation to solve for t, or in the y equation to solve for t. Which one? X. Makes it easier, right? Go easy on yourself. Okay? So I'm going to solve the x equation. Or did you say x?
Yeah.
That's the easy one to solve for t?
I thought so.
You sure?
I was just what Paul told me.
So walk me through how you would solve that one for t.
I was just guessing because no one else.
Well, walk yourself through. How would you solve that one for t?
I was thinking I would add 9 both sides.
Okay.
And square, and then you'd have
Square?
X plus 9, or square root.
Square root?
X plus 9.
Okay. Walk me through the other one.
Subtract 1 and divide by 2.
Which one's easier? No.
Probably the y one because you don't have to deal with the square root.
You don't have to deal with the square root. Yep. So I'm going to solve y equals 2t plus 1. I'm going to solve that for t. So I'm going to subtract 1, and I'm going to divide by 2. Now I'm going to take that and I'm going to put it into the other equation. So my other equation was x equals t squared minus 9. So that's going to be x equals t, which t is 1/2 times y minus 1. Then square all of that, and then subtract 9. One half times the quantity y minus 1, then squared. I square the first part, right? And I square the second part. It's just like any of those over there on the sideboard. 3y quantity squared is 3 squared times y squared. xy quantity squared is x squared times y squared. So this one becomes x equals 1/4 times the quantity y minus 1 squared, and then minus 9. Now, we've seen this before. Mathematically, what would that equation produce for a graph? What's it produce mathematically when I graph it? An equation with one squared variable. What graph is that?
Parabola.
Parabola. Okay, so it's going to produce a parabola. Which way is my parabola going to open? Nope. Nope. Which way is it going to open?
To the right.
Why to the right?
That's we graph.
Because that's what we graphed, right? Exactly. Exactly. You are the first person today to pick up on that. We graphed a right opening parabola. We just chopped it off. We only gave a little section of it. Okay? So this graph down here, back from our conic sections unit, is a right opening parabola. Y is squared with a positive a value is a right opening parabola. Okay? If I were to graph this box on the graph, it would look like that, except it would extend and keep going on forever, like that. Okay? What I would like you to do now is I would like you to make a table, graph it, and then eliminate the parameter. I'll handle the verifying it on your calculator. Okay? Because we'll just do that together. Okay? So my t values go from -2 to +3. If I plug those values into my x equation or my x function, I get -1, 0, 1, 2, 3, and 4. If I plug those t values into my y equation, I get 0, -1, 0, 3, 8, and 15. Graphing those, I got here, 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 1, 2, 3, 4, 5, 6, 7, 8, 15. So I get that. I know I want to put an arrowhead on that, and I want to keep going past it, but no mas. Okay? So that's my picture. Now we need to eliminate our t, eliminate our parameter. I'm going to go with x equals t plus 1 first. I'm going to say that x minus 1 is equal to t. Then I'm going to say that y is equal to t squared plus 2t. And then, so that becomes y is equal to x minus 1 quantity squared plus 2 times x minus 1. X minus 1 quantity squared is x squared minus 2x plus 1 plus 2x minus 2. So I get y here is equal to x squared minus 1, which is an upward opening parabola shifted down 1. Now, very quickly, let me show you on the calculator how this works out. We will do a lot of this tomorrow, so I'm going to first change this to parametric. Then this becomes t plus 1. This becomes t squared plus 2t. I change my range here from -2 to +3, and there it is. Now, if I take my window and I make my window be the exact same as what was on the smartboard, I see I get the exact same one. Now, the magic that is how I can do this. I'm going to switch back to a function. I'm going to go down here because I like it to be a different color. X squared minus 1. Shabam, there it is. Now watch this. If I take this away, I should cover up my parametric function, because my parametric function is just a portion of the actual equation. Okay? So we got that going for us, which is nice. Thanks for playing along. Tomorrow, listen up quick, everybody freeze. Tomorrow, if you have a graphing calculator, bring it charged tomorrow, because we're going to be doing this stuff on graphing calculators tomorrow.